Thank you so much. And thank you so much for the invitation to be here today. It's a real pleasure. I have come all the way from Australia, which is a bit of a journey. So hopefully you'll give me a couple of hours to speak instead of the 25 minutes that I've been allotted. I study the East Australian Current, which is a western boundary current of the South Pacific subtropical gyre. I feel like a bit of a fish out of water, if you pardon the pun. But we're going to be talking about the East Australian Current and what we've learned about how to model it and how to observe it, sort of closing the observational gaps and reducing uncertainty. And hopefully some of what I show is relevant to the tropics and some of the ecosystems that we've been discussing and will discuss. At least the methodologies are potentially readily applicable. And I acknowledge that this is a huge team effort. I've been doing this work for 20 years, and it's certainly not on my own. I have a team of 20 people, and they've all contributed over the past many years. So I'm going to start with the take-home messages in case I run out of time. So the things I want you to know are that we need to observe the ocean. We need to close those observational gaps to reduce our uncertainty. And I want you to remember that all models are wrong, but some are useful, right? I'm an observationalist. I'm here to keep the modelers honest. What we've been learning recently is that observations in the subsurface are extremely important. They're also very hard to find, hard to come across. We need to be observing in highly variable regions. Typically, people observe where it's easy, quiescent regions, quiet regions, regions where the flow is coherent because it's easier to do. But we need to observe in the regions of high variability if we're going to constrain the models in that way. We need a feedback loop between the models and the observations. The observations inform the models inform the observations, and we need to work together, the observations and modelers, to improve both the observation system, the observing system, and the modelling system. I'll touch very briefly on the next frontier, the submesoscale. I'll probably run out of time by the time I get there, but observing the submesoscale is challenging, but we need those submesoscale observations if we're going to improve our models at those scales, so cross scales. And then, very finally, we need to link into global efforts in observation and prediction, and this is a wonderful initiative to do that, right? What a diverse group of people. It's very exciting to see the diversity in the room, the diversity of thought and ideas. So I really applaud Julian, the organisers, for bringing this team together. So where are we? The East Australian Current. We are the western boundary current of the subtropical gyre in the South Pacific. Here we go, the tropics up here. Current comes down the coast and sheds diverse, large mesoscale eddies. What's really important is interaction of that current with the shelf and then the coastal regions. It has a huge impact on the region. It's also an ocean warming hotspot. This is a map of Australia. This is SST trend, and this is quite a large trend, 1 degree per decade. It's warming at one of the fastest rates on the planet, which is quite significant. You might also notice there's patchiness here. And I think that's important, right? The regional processes cause patchiness. Warming is non-uniform. So you can't just average it up and say it's warming, because there are regions that are not warming. There are regions that are climate refugia. There are regions that might actually be flourishing in this warming ocean. And for all these reasons that you all know about, we need accurate observations and accurate models. So, how do we observe a dynamic western boundary current region? I've been leading the ocean observing program along the east coast of Australia for the last 20 years, and we have a whole range of observations. No single observation type is perfect for everything. Yesterday, there was a lot of talk about sea surface temperature or sea surface properties. Yes, we can get sea surface properties from satellites. That's fantastic. We can get global coverage of the top centimetre of the ocean, right? That's what a satellite measures, the temperature in the top centimetre, or smaller than the top centimetre of the ocean. We need to remember that. The ocean is on average 4 kilometres thick or deep, right? Satellites can't do it all. We need Argo floats for the deep ocean, deep Argo. We need XBTs, expendable bathythermographs, for repeat lines. We need those repeat observations across the one location. We need moorings for detail and accuracy for the climate signals for our trends, to resolve our trends and our extremes. We need coastal radar and coastal gliders for that spatial coverage. It gives context for our high resolution mooring observations and give the spatial coverage and the context, and it can also pick up extremes. And then, of course, we need our ocean models. I put it right down the bottom because I'm an observationalist. This is the East Australian Current. So we have this whole network of, this whole range of observations in the system. We have a deep water transport array with moorings down to 4,000 metres. We have coastal radar. We have gliders coming down the coast. Here we have the trajectories of about 60 glide emissions over the last 10 years or 15 years coming down the coast. I said we need to observe regions of variability. We can't do quiescent long transects in a very dynamic western boundary current. So we have to zigzag down the coast here. So you can see it looks like a dog's breakfast, as it were. It's a real mess, but the observation is actually really valuable. And with repeat missions over the last 15 years, we can pull out extreme events and look at anomalies, etc. We've got hydrographic time series back to the 1950s through the water column with depth, and then mooring observations in the last 20 years. And all of that comes together to provide a very comprehensive ocean observing system, which helps us improve our models. Okay, so we have a modelling system, the CCOFS modelling system, the Southeast Australian Coastal Ocean Forecast System. We nest in our near global models, 10 kilometre resolution or 1/10 of a degree. We downscale into our regional ROMS model, Regional Ocean Modelling System, 2.5K to 5K resolution, so 2.5K across the shelf, 5K in the alongshore. And then we have higher resolution grids again. These are all 750 metre to 1 kilometre grids, and then down into Sydney Harbour at 50 metre scales. And so this is the backbone of our modelling system. I'm not going to go into any details, which is probably unsatisfying for most of you. But we have a range of simulations. So we have multi-decadal, 30-year regional ocean modelling runs. We have very high resolution assimilation experiments. We have a long assimilation. We have observing system simulation experiments. And this is kind of the workhorse of our modelling program. We've used our models to understand a whole range of dynamical processes in the system. They're all listed there: regional processes, coastal upwelling, shelf circulation, boundary current separation. Where the East Australian current separates from the coast has a big impact on the circulation downstream. When it separates, these large mesoscale eddies form, and where those eddies form determine the circulation and the warming along the coast. We're looking at warming trends, eddies as drivers of ocean warming, etc. So marine extremes, both in temperature and salinity. So river plumes, freshwater outflow, drive marine extremes on the coast for us. And then, of course, the biological piece in a physical model, Lagrangian connectivity, the transport of particles, pollutants, larvae, eggs, spores, blue bottles. We're working Portuguese man of war and using it for marine park design, etc. So all models are wrong, some are useful. Right? I said the surface is easy, and that's due to widespread surface satellite data. So here's just one example of a cross-section through our model. This is the east coast of Australia. This is the East Australian current. This is one of those large mesoscale eddies. That's 3 degrees, so it's a big eddy, right? A few hundred kilometres wide. These are 3 different models. This is a ROMS 40 VAR data assimilating model. This is, our 10 kilometre resolution parent model that we nest inside. And this is our ROMS free running model. And what we see is temperature and obviously the stratification through the water column. And ideally they all look the same, but you can see that none of them are the same, okay? They're all different. So the depth of the eddy changes, the stratification changes, the slope of the isotherm changes. That's going to affect your heat content in the ocean. If you don't know the heat content, how do you know about ocean warming? So we need our models to be better, and we need them to be better below the surface so we can look at climate change trends, extremes, upper ocean heat content, transport of heat, heat variability, etc. Even the mixed layer depth, so stratification, mixed layer depth, they're not right in these models, and it's very difficult. But without observations, you don't know if they're right, and you can't improve your model. So, as I said, getting these models right is essential for understanding climate change and trends in the system. So we've spent a lot of time trying to improve the quality of our ocean models. This is a really nice paper led by Colette Kerry, a researcher in my team, in the Oceanography Society Oceanography magazine. So we've brought data assimilation to Oceanography magazine, which is kind of cool, where we looked at 3 different ways of observing the impact or assessing the impact of observations on ocean models. So we have this really comprehensive observing system. We have a really nice modelling system, and we want to know how the observations inform our model, how the observations improve our model. So we use 3 different methods to assess the impact of our observations. We use the ROMS 40 VAR adjoint, which I'm not going to go into today. We use observing system experiments where you compare different observations that are assimilated into the model. So you might have model A has a simple assimilation system, and model B, which has very complicated observational system. And you compare the results of the two, sort of what I showed on the previous slide. And then we have observing system simulation experiments where it's all synthetic. So you have model A and model B. You assume model A is the truth, which we know it's not. And then we assimilate observations from model B into model A and see how it improves. So it's a whole synthetic, potentially a digital twin environment. And so we use these three different methods to compare how our observations improve the quality of our models. And each of the methods gave us the same answer. That's nice. We need subsurface observations, and we need them in regions of high variability. Okay, so that's the take-home message: subsurface observations in regions of high variability. I can flick through some slides that prove what I'm going to say, but we cannot get into the details, so you probably won't really believe me anyway. But we have a whole bunch of papers that sit behind that little synthesis paper. So we've been doing these observing system simulation experiments, assessing observations, how to improve our models for many years. I'll show you three results, one result from each paper, looking at the impact of assimilating. And by data assimilation, I mean you have a model, you have an observation, and you force the model to match the observation. So it's not actually dynamically consistent anymore, but it hopefully represents the ocean in a better way. So these OSSIs, observing system simulation experiments, are completely synthetic. There's no real ocean in this example. But we take synthetic observations of subsurface temperature and we assimilate them into our model. And we do it in 4 different ways across 4 different experiments, and we look at the results. This one here has no subsurface information in it, and this is an RMS in temperature. So the higher the red, the darker the red, the worse it is, okay? So this is when you're just using surface observations. All this conversation yesterday about sea surface temperature and satellite data, it's the worst of all of them. When we start to include subsurface information in dynamic regions, the results get better. So that red colour gets lower, the RMS lowers. So subsurface observations are key to improving prediction, particularly in dynamic regions. If we want to look below the surface, I've talked about ocean heat content. Let's look an eddy. This is 2,500 metres down, so 2.5 kilometres deep. This is a vertical slice through a mesoscale eddy. Again, 4 different experiments assimilating data in different ways. In this instance, white is the best. So this is a difference plot. So we want to see the difference is 0 between what we think is the truth and what our experiments show. This is when we assimilate just surface information. Red, big difference, not good. When we assimilate observations in regions of variability right through the eddy, we get a much better solution. So subsurface observations are key to improving the subsurface. Go figure, right? It sounds like a no-brainer, but people haven't been doing it. So vertical structure of eddies is poorly represented, but subsurface observations improve them. So there's 2 different results, 2 different papers there. The third result is looking at how frequently we need to observe, right? So we looked at the frequency of observations in half a year, 90 days, 14 days, and 7 days. Blue being the 7 days, compared to the variability in the system. So if you have a highly variable system, you need to observe frequently. That makes sense as well, right? Because it's highly variable. So again, sounds like a no-brainer, but we were able to show that more frequent observations assimilated into a system improves the representation of the variability in the system. So you need to observe frequently and you need to observe below the surface. So basically, we need more data, right? We need more observations. Everything, everywhere, all at once. It's a bit of our catchphrase in my team. We need lots of observations everywhere, all at once. This is Australia's, well, it's not even, it's part of Australia's economic exclusive zone. This is the density, observation density around Australia, up to 10 data points in every grid cell on average per month. And we've had a sustained ocean observing program for the last 20 years that has cost multiple hundreds of millions of dollars, right? Look at the observation density. It's pretty bad. So we need more subsurface observations. Models are only as good as the data we have. Patchy observations is poor quality models. So I looked at this map, and it's pretty sad, and I thought, what can I do? What can I do to help change this map? Well, I can't do a lot. but the fishing community can. Look where they fish. That's the fishing effort around Australia in our economic exclusive zone, in coastal regions. That's huge. So I set up a program to leverage the power of the fishing community, and there are lots of fishes in tropical ecosystems, let me tell you this, right? We're going to leverage the power of the fishing community to collect subsurface temperature observations everywhere all at once. So we came up with a system. It didn't exist, right? Fishers want to go fishing. They don't care about oceanography. They don't want to measure ocean temperatures. They don't want to do anything that's going to impact their day. So we needed it to be completely autonomous. We've got to put our temperature sensors onto the fishing nets. They've got to stay there. When they come back on deck, they've got to transmit autonomously. When they get onto the deck, data has to go to the cloud autonomously. And then you know what we've got to do? We've got to give the observations back to the fisher, the people that collected, and tell them what you do matters. Right? You are making a major contribution to understanding the ocean. Your data is going to go to the global telecommunication system and improve tropical cyclone prediction, and you can use it to improve the quality of your day, to improve your catch, to fish smarter, not harder. So the first thing we did was promise the fishers we'd give the data back to them. And we've got to do it in the matter of minutes. So we came up with this idea where everything's got to be full circle, right? So transmit the data, round into our database, quality control it in Amazon Web Services, send it back to the fisher, and if you can, integrate it into the ocean models as well. Give them a forecast for tomorrow. Tell them what the ocean's going to be like tomorrow so they can catch their fish, so they get a subsurface estimate of thermocline depth, which is really important for many fish species. And we did it. We designed a system that works. Thanks to my colleague, John Radford. I'm not going to go into the details, but it's a research quality sensor. The data flows to Amazon Web Services in real time. I get the emails on my phone every time a fisher goes fishing. So we have this little deck unit, which is the secret recipe there, and that transmits all the data. So this is the annual mean number of Argo floats around Australia. You see that? It's down at 10. Anything, the light's not great. Blue is no data, which is hard to see up in this region through the maritime continent. Indonesia, not many Argo floats up there because it's too shallow. Less than 10 is white. And just a little bit more than 10, you can see a couple of dots there. Or this is the Argo program over the last 20 years. This is us over the last 3 years, okay? So open access data around Australia, New Zealand, and now increasing across the tropics. You can't really see, I'll zoom in on the next slide, but we've got Papua New Guinea, Samoa, Solomon Islands, Tonga, where else? Papua New Guinea, Fiji, right? Okay, let's have a look at Fiji. Oh, before I go, this system goes on anything, right? It can go on a multi-million-dollar purse seine net, that's in Papua New Guinea, or it can be a sea country ranger, an Indigenous owner out there collecting data to empower them to measure their ocean territory, scallop dredge, 1,000-metre fish trap, etc. So we have them on all sorts of vessels around Australia and around the Pacific. This is our data coverage up in the tropical Pacific, so Papua New Guinea, Solomon Islands, Fiji. We instrumented our first vessel in Fiji in May this year. May, look at this. The data coverage that we're getting, this is 14 degrees of latitude from 9 tuna longliners in Fiji are contributing open access data to the global telecommunication system to improve tropical forecasts, tropical cyclone prediction, as well as fisheries management, catch management, and subsurface ocean temperature to improve the quality of my ocean models, which is where I started this program. So this works everywhere and everywhere. And you can see this data from May through to September. You can see through the water column, we're down at 500 metres because that's where the longliners fish. You can see the thermocline, you see the stratification, you can see the seasonal cycle. And then we compare the data to the models, okay? I said the models don't work below the surface. This is all our data. This is a European model. We pulled that out for fun because we're in Europe. The model is too warm below the surface. Okay, so the thermocline is not being represented properly. The heat content is not right. How are we getting our estimates of ocean warming correct? And then down at the bottom, it's too cold. So this is all the data along the east coast of Australia. Here's another example. This is back to an experiment we did before we started the program. We wanted to see would the model actually improve if we had these observations. So we took the fishing density around New Zealand and had a look and looked at the bottom temperature improvement and the heat content improvement. In this case, red is an improvement. And we see that we're getting significant improvement in bottom temperature, which is important for fisheries, in ocean heat content, which is important for climate change, understanding the impacts. So we did a lot of experiments before we started the program. And now that we actually have real data, this is back to real data, We're now assimilating the data into our regional models, and you can see, this is our model here, not much structure. This is our temperature data, lots of structure. So mixed layer depth, 2 mixed layers, seasonal variability, etc. And then when we assimilate the data, in this instance, white is a reduction in error. And this is a trace of a long line. So it goes down in the water for a long period of time, a long distance, and then up again. So we're getting a lot of subsurface ocean temperature data. So it's actually a really valuable way of getting this information. And it's not just for big multi-million-dollar vessels. This is Carol. She's a traditional custodian of sea country in Northern Australia. We've been out with her on a vessel. She's taking profiles, right? So this is the Tiwi Islands up off the Northern Territory, very remote region of Australia. This is her data that she collected, down to 55 metres depth, etc. And I really acknowledge the traditional custodians of our land and the Tiwi Islanders that we've been working with on a marine parks project. And this is the comparison of her data with Australia's ocean forecast, right? They're supposed to look the same. This is our Bureau of Meteorology ocean forecast for the region. This is the data that we collected. You can see the stratification's not right. So they're missing the temperature at the surface. This is temperature and depth. Missing the warming at the surface, missing the cooling at the bottom. It's too well mixed in the ocean model. Okay, so this is the first open access data ever from that region. And we're out there with sea country rangers collecting open access information and traditional custodians. So we started with the observing system. We integrated the data into our models. We saw the models weren't great. We thought about how we can improve our models, right? We collected more ocean observations. We set up a whole new observing program, right? And we integrate it back into the models to improve the quality of the models. So we've got this full feedback loop. And don't get me wrong, we go out on ships. I spent a month on the RV Investigator leading a team, but I don't really want to go out for a month every year or every month, right? So we have all these platforms all contribute to improving our understanding of the ocean. So we have a comprehensive observing system. We assimilate the data. We improve our models. Gives us information on the observing system on where to observe and how to observe it. And we go in and keep improving. I'm going to touch very briefly on salinity. That whole thing was about temperature. It's a lot easier to observe temperature than it is to observe salinity. And also the east coast of Australia is fairly arid until the triple dip La Nina of 2021, 2022, etc. Then all of a sudden we had more rainfall than we'd ever seen before. And we had to start observing salinity in the coastal ocean. This is a glider line. So I said we had these sustained glider lines down the coast. We'd been doing it for 10 years and never seen anything particularly exciting. And all of a sudden, we've got these freshwater plumes. And by fresh, it's like 34.6. It's not that fresh. Sorry, 30, yeah, anyway. But they're extending 70 kilometres offshore. But these river plumes, or freshwater outflows from the rivers, contain contaminants, sediments. Cows and houses were washing down the rivers. You imagine what that's doing to the oceanic environment. So by having a sustained glider program, sustained observing system, we're then able to look at the extremes. You can pull the extremes out and analyse them. And we use the marine heat wave paradigm where you're looking at your 95th percentile or 5th percentile to show what an extreme freshwater event looks like. We haven't quite got fresh water into our models. We've done some idealised studies. A lot of people are further ahead than us. But I can show you, comparing our glider observations with our model in TS space, again, they're supposed to look the same, right? They don't look the same. The extremes are not captured in our model. So the freshwater extremes, these extreme events driven by extreme rainfall, are not well represented in the model. And that's a work in progress for us. How do we improve the quality of the freshwater information that's coming into our model? And perhaps it's not something I can solve in a hurry, but we're working on it. I mentioned the sub-mesoscale as the next frontier. No one's mentioned the SWOT satellite mission, surface water ocean topography. It's just changed the way we see the surface of the ocean, all the sub-mesoscale, fine-scale dynamics. This is a model, but this is what SWOT is actually showing us, really fine-scale information. This here shows AVISO observations of sea surface height. This shows SWOT observations of sea surface height. So it's a real step change in how we observe the ocean. But unfortunately, it's only every 21 days, the repeat cycle. So how do you integrate information that's very high resolution, but only every 21 days? Basically, we need SWOT everywhere at all times. And so we're working on Looking at the observation impact, how do very fine scale resolutions of sea surface height improve our understanding of the ocean and our ocean models? And what I can say is, again, without going into the detail, we have again a bunch of different observing system experiments from our model. When we integrate or assimilate high resolution SWOT observations into our ocean model, we get a better prediction down under the surface. It's projected into the interior of the ocean, which is remarkable. So these are actually observations for a month at sea on the ship, all distilled, 1 month at sea, distilled into one little subplot. Not so fun. But we get really good estimates of the fronts. They're steeper, they're more realistic. And that's the ocean surface sub-mesoscale information at the surface of the ocean assimilated into the ocean model, projects down into the ocean interior and gives us a better representation of the subsurface fronts. And this is a challenging region, as I said. The East Australian current's really complex, and this is across a high resolution or fine scale eddy and a front there. So regional processes really matter. We did a paper looking at warming and western boundary currents of the South Pacific, of the Southern Hemisphere. So we did all 3 western boundary currents. And when you look at a global map like that, and red is warming and warming trends, it looks pretty red, right? It sort of looks like the whole of the ocean is warming. But when you zoom in, you see it's not really red everywhere. So this is upper ocean heat content trend. This is mixed layer depth trend. And I've just told you how bad models are. And then I present to you a model, so I apologise for that. But this is what we're trying to work out. Here, negative, blue is a negative trend, right? So we've got warming trend in upper ocean heat content, a warming trend or a deepening in of a mixed layer depth. Here we're getting a reduction in our mixed layer depth and a reduction in upper ocean heat content. So regional processes can determine what's going on. Of course they can determine what's going on, but can vary. And we saw this in the Peru talk earlier, right? 2 systems that are connected, but are showing a different response to climate change. This region here is not warming as fast as this region here because of a southward penetration of the East Australian current, a southward penetration of the subtropical gyre, a reduction in variability, and we saw all this in our global paper, but we're getting a reduction in variability in this region, and so it's not warming as fast. So if you have islands, and we have tropical islands up here, perhaps they're not, things aren't as bad as we thought, perhaps. So regional processes matter, we need to resolve them and we need to consider them. So in summary, what to observe? To close our observational gaps and reduce uncertainty, we need sustained long-term observations for the climate record, so Argo and moorings is really fundamental. We need spatial variability for context, and just remember that all models are wrong, but some are useful. Some are more useful than others. We need our subsurface, and we need it in variability-rich regions, right? So temperature and salinity. Observation, location and type matter. Not all observations are made equal, all right? And don't underestimate the power of research quality, crowdsourced citizen science data. It's very, very powerful and very low cost, and it's really doable in tropical regions. So consider crowdsourced research quality data seriously. This is me in Papua New Guinea on a purse seine. I've been to Papua New Guinea twice this year, which has been a phenomenal experience. We need a feedback loop between our models and our observations to improve the quality of both, and better observing system design comes out of integrating the model, our observations into your model and looking at the results quite closely. Obviously the sub-mesoscale is the next frontier, but it may or may not be important in this room, but we need fine scale observations to actually constrain our models at that scale. And link with global efforts, and this is a really good initiative to do that, right? We can't do it on our own. The Coast Predict is a global initiative to improve our coastal predictions and improve observations in coastal regions. And we have 2 of our projects are endorsed under the UN Ocean Decade. And with that, I will finish.